this tutorial, we are going to talk about periodic trends. So first we're going to talk about the trend in atomic radius, and then the trend in ionization energy, and then finally the trend in electronegativity. So let's start with our trend in atomic radius. So as you may have guessed, an atomic radius is the distance from the nucleus of an atom to its valence electrons. Another way to think about valence electrons are the outermost electrons. So if you're looking at an atom and you're wondering what the atomic radius is the distance between the nucleus or from the nucleus to the outermost or the valence electrons. As you can imagine, this is difficult to measure because atoms are not circular or spherical according to the quantum model. They are funky shaped, and since the electrons are only located in the outer orbitals based on probability, it makes it very difficult to measure from the center of the nucleus to the outermost electrons. So to measure atomic radius, you do it like this. You take two atoms and you bond them together. So for example, you might say take two hydrogens and bond them to each other. And then you measure the distance between the two nuclei, so that's the distance, and then to get the bonding atomic radius, you take the distance and divide it by 2. So that's how we actually get an atomic radius. Okay, so let's talk about the atomic radius trend as you go across a period. So as you go across a period, so for example, let's use period 2. You may remember that the period number, or the rows that go across, indicate the number of energy levels that an atom has. So all of the elements in period 2 have 2 energy levels. So we can look at, say, lithium, beryllium, boron, and we could keep going through carbon all the way to neon, but I'm not going to show you all of them. I'm only going to show you these 3. So they all have 2 energy levels, which might make you think that they would have the same atomic radius. But the fact is that they don't. They have different atomic radii. And so lithium's atomic radius is actually bigger than beryllium's. Beryllium's is a little bit smaller, and then boron's is even smaller, and then as you go across the table, you get smaller and smaller radii. And there's a reason for that, and you need to know the reason. And the reason is the number of protons in the nucleus. You'll notice that lithium has 3 protons in its nucleus, beryllium has 4, and boron has 5. And they all have the same number of energy levels, and they also have the same number of core electrons. They each have 2 electrons in the core. And so what ends up happening is that the number of valence electrons doesn't really matter because those valence electrons are not blocking each other from the nucleus. So really what it boils down to is that your atoms all have 2 energy levels, but they each have different numbers of protons pulling on those energy levels. And as you know, opposites attract, and so those energy levels are just getting slightly more and more closer and closer to the nucleus as you go across a period because of the increasing number of protons in the nuclei of the atoms in a period. So the trend across a period is that the atomic radius decreases as you go from left to right across a period. So as you go down a family, for example, family number 2, as you go down a family, you have beryllium and then magnesium and calcium. And what they have in common, you may remember, is that they all have 2 valence electrons. But that's not what gives them their atomic radius. What gives them their atomic radius is partially due to, of course, the number of protons in the nucleus, but it's largely due to the number of energy levels that they have. And you'll notice that beryllium has 2 energy levels, magnesium has 3 energy levels, and calcium has 4 energy levels. And so you'll notice that as you add an energy level, you're actually making the atom larger. So when you go down a family, you will find that the trend in atomic radius is you get an increase in atomic radius. And the reason why is that you're adding an entire energy level of electrons as you go down a family, which is just going to make the atom get bigger and bigger. So again, the trend as you go down a family is you're going to get an increase in atomic radius as you go from the top of a family to the bottom. Okay, so here's a summary of what you see in the trend of atomic radius. So as you go from left to right, you're going to get a decrease in atomic radius, or you could say as you go from right to left, you will get an increase. And as you go down a family, you get a decrease. And so the generalized trend, as you go from the upper right-hand corner to the lower left-hand corner, you will get an increase in atomic radius, which makes helium your smallest atom and francium your largest. All right, the next trend we're going to talk about is this trend called ionization energy. And the definition of an ionization energy is the amount of energy required to remove a valence electron from an atom. So if you think about it, it makes sense. A valence electron, so any of these outer electrons, are attracted to the nucleus. They want to be close to it. And so there is a certain amount of attraction or energy that holds them into the atom. So ionization energy is the amount of energy that it would take to actually pull that electron off the atom and overcome this energy of attraction. So I think it goes without saying that if you have an electron that's really far from the nucleus, it would take less energy to remove it because it's so far from that force of the pull of the nucleus. So it would have less ionization energy. And then, of course, an electron that's closer to the nucleus is going to be much harder to remove because it's being pulled on by the nucleus a little bit more, and it would take more ionization energy to remove it. So the trend as you go across a period. So remember, with atomic radius, our atoms as you went across a period got smaller and smaller because of the pull of the protons in the nucleus on those energy levels, because they all have the same number of energy levels. So if you think about it, if we're trying to remove, say, a valence electron from each one of these, those valence electrons are going to be harder to remove the closer they are to the nucleus. So it should be harder to remove, say, for example, in period 2, the further to the right you go, the harder it is to remove an electron because you're just getting closer, your radius is getting smaller and your electrons, your valence electrons are getting closer to the nucleus. So you should see a trend of an increase in the ionization energy because like I said, those valence electrons are getting closer to the nucleus, and so it would require more energy to remove them the closer they are to the nucleus. So again, why? Because as the radius decreases, the valence electrons get closer to the nucleus, so they become harder to remove and require more energy. So the trend in ionization energy as you go across a period is that it increases as you go from left to right. And so the same thing applies as you go down a family. Remember, as you went down a family, you got an increase in atomic radius because you're adding a whole new energy level. And so the energy required to remove an electron or valence electron from the outer energy level, so either any of these electrons, gets easier and easier, less and less energy as you go across because your radius is getting smaller or larger and larger and larger. And so those electrons are further from the nucleus and it's easier to remove them, so it takes less energy. So as you go down a family, you should see a decrease in ionization energy as you go from top to bottom. So here's a summary of the trend in ionization energy you see on the periodic table. So as you go across a period, you get an increase in ionization energy. And as you go down a family, you get a decrease, or you can say as you go up a family, you get an increase. So it's the opposite trend that you get with atomic radius. And of course, if you go from the lower left-hand corner to the upper right-hand corner, you get a generalized increase in ionization energy, which makes francium the easiest to remove an electron from, and helium the hardest atom to remove an electron from. The last trend we're going to talk about is electronegativity. And electronegativity is a measure of an atom's ability to attract electrons. And we're talking about not only its own electrons, but electrons from another atom. So just like with the other trends, there are a couple of things that will affect something's electronegativity. So one of the things that will attract or affect electronegativity is the number of protons in the nucleus, the charge on the nucleus. And then the second part is how far away the electrons, either the ones they already have or the space for new electrons, are from the nucleus. And so you can imagine that an atom's electronegativity would increase. It would have a higher ability to attract electrons if it had space closer to the nucleus and if there were a lot of protons in the nucleus. So you're going to start to realize that all of these trends are very related. So as far as electronegativity is concerned, it's really related to radius. So remember, as you go across a period, and so in this case we're doing period 2 again, from lithium all the way to neon, your atomic radius gets smaller and smaller and smaller. And so what that means for electronegativity is that the atoms become more and more able to attract electrons. And it really is just about the distance from the valence energy level to the nucleus. So you're going to get an increase in electronegativity. So you might ask why. It's because as the atomic radius decreases, the valence energy level gets closer to the pole of the nucleus. And so the atoms become more able to attract not only their own valence electrons, but electrons from another atom. So the trend becomes that you get an increase in electronegativity as you go from left to right across a period. And of course, down a family, you get an increase in atomic radius, which means that the valence energy levels get further from the pole of the nucleus. So you're going to find that you're going to get a decrease in electronegativity because those valence electrons are further and further from the pole of the nucleus. So the electrons, the valence electrons, are less attracted to, or those atoms are less able to attract their valence electrons and any other electrons maybe that come in from another atom just due to sheer distance from the nucleus. So again, as you get more or a larger atomic radius, the valence energy level just ends up further from the nucleus, and so the atoms become less able to attract electrons, either their own or someone else's. So the trend in electronegativity as you go down a family is that you get a decrease as you go from the top of a family to the bottom. All right, so there is an exception to the electronegativity trend that we need to talk about. So on your periodic table, there is this family called the noble gases, and they are family 18. Family 18 has no electronegativity. So their electronegativity values are equal to 0, just the noble gases. And the reason for that is because with electronegativity, part of electronegativity is the atom's ability, if you remember, to attract electrons from another atom. And the fact is that your noble gases don't need to attract electrons from another atom because their valence energy levels are full. So they have a full valence energy level. And what that means is they don't have any room for electrons or any more electrons. Therefore, they don't have an electronegativity value. So you need to remember this exception to the electronegativity trend. All right, so let's summarize our trends in electronegativity. So as you go across a period, you get an increase in electronegativity, and as you go down a family, you get a decrease, which is the same as saying as you get an increase as you go up a family. Now remember, there is an exception. Your noble gases, I'm just going to cross them out because they have zero electronegativity, which means that if you want to do a generalized trend, the generalized trend in electronegativity is you get an increase from the lower left corner to the upper right-hand corner with the exception of your noble gases. So that makes francium the least electronegative element, and you must know that fluorine is the most electronegative element on your entire periodic table. It is the most able, fluorine, to attract electrons to itself as well as to hold on to its own electrons. So again, you must remember that fluorine is the most electronegative element on your periodic table. That concludes this video on periodic trends.